Chapter 17 and 18 have similarities and differences. The major similarity between the two chapters is that we're dealing with nominal data. We're dealing with people or things or places that have been classified into categories. So we're dealing with frequencies, we're dealing with proportions, we're not dealing with means, standard deviations, sums of squares, that type of data, because we only have counts of data or counts of people. One of the differences is that in Chapter 17, people or places or things in the categories where we had the frequencies or the counts or the number of people. In Chapter 18, we will change those counts into proportions. So if 10 of 100 people feel a particular way, we would be dealing with 10%. So you'll find that the data actually are proportions or percentages rather than frequencies, even though we will get the proportions from the frequencies. The second difference between chi-square, Chapter 17, and the binomial test in Chapter 18 is that chi-square is a statistic that you use when you want to compare 3 or more categories. Compare the frequencies in 3 or more categories, where the binomial test classifies people into 2 categories. We have yes versus people who have said yes versus people who have said no. People who agree with the particular policy of the president and people disagree, such as we have in the opinion polls. People who approve of a particular product and people who disapprove. Winners versus losers. So that's where the name binomial comes from. By to nomial name, we have 2 names or 2 categories. I'm going to go through these slides pretty quickly so I can spend more time on the problems. We have 3 problems at the end. So the binomial test, it provides data for testing hypotheses about population proportions. We'll be given a population proportion, or someone assumes that a proportion is a particular value, and we'll want to test whether that hypothesis about the proportions is correct. So binomial, because individuals or places or things have been classified into 2 categories. The population proportion, we'll use the letter P, and the complement of that will be the letter Q. P plus Q must always equal 100%. We have 2 categories. If 75% of the people agree, 25% must disagree. So Q equals 1 minus P. If P is 60%, then Q must be 40%. The null hypothesis specifies values of P and Q. We'll only write our null hypotheses so that they specify values of P, and we will always do 2-tailed tests using the binomial distribution, and our statistic will always be the Z statistic. You can use T. If you have small samples, we'll be using Z. Most of the time, tests of proportions have rather large samples. So again, individuals will be classified. Our sample symbol for our sample size is N. They'll be classified in either categories A or B, agree or disagree, or whatever terms we're using. And the sample statistic, X, is simply the number of individuals classified in category A. If we take a sample of 100 people and 40 people agree, then X is 40. 60 is the complement of that. We'll write this should be a square root sign, and we'll be writing our formula slightly differently. We'll have Z equals X divided by N, which is the sample proportion, minus P, the population proportion, divided by the standard error of the proportion, which is PQ over N. And remember that Q equals 1 minus P. So this formula should look similar to you. Our numerator is a difference between a sample proportion and a population proportion. And our denominator is what type of difference would we expect, the expected difference for a sample of a certain size when we have people classified in two ways. We find a difference, we have an expected difference, and we want to know whether this difference is due to sampling error or whether there really is a difference between our sample proportion and our population proportion. We'll be using formula 18.2. Your book gives you two formulas. There's formula 18.1. I find formula 18.2 easier to use. The logic underlying the test is similar to the logic that we've used in all the test statistics that we've run. We compare a sample data with some hypothesized value. If the data are consistent with the hypothesis, we conclude the hypothesis is reasonable. If there is a large discrepancy, we reject the hypothesis, conclude that it's not reasonable. The binomial test will follow the same four-step procedure. We state the null hypothesis, we determine the critical value and locate the region of rejection. We'll be using the z-table, table of the normal curve. We calculate the test statistic, and then we make a decision to reject or not reject the null. There are two assumptions that underlie this test. We have independent observations. If you were asking the survey to one person, you would make sure that that person's information is independent of the second person that you asked. That one person isn't influencing another person in your study. And secondly, we have to have frequencies greater than 10 to justify using the normal table for determining critical values. We have to have a reasonably large sample size. Your book goes over these assumptions. In football games, and baseball games, and basketball games, does the home team have an advantage? Does the team that's playing on its field or in its stadium or on its court have an advantage? We often feel that the home team does. A particular researcher decided to test this out. On a Saturday, he watched or recorded 64 football games. And of those 64 games, 42 were won by the home team. We have a binomial distribution. We have the home team and the away team. Two categories where they're playing. The home team won 42. So the sample proportion equals 42 divided by 64, or 66%. This is our sample proportion. What's our population proportion? Well, if there's no home team advantage, then the population proportion would be 50%. If there's no home team advantage, then whichever team wins, it's a matter of chance. It's 50-50. That's what we would expect. That's the assumption, that if there is no home team advantage. So our null hypothesis is that there is no home team advantage, and our alternative hypothesis is that there is. So we would write our null hypothesis, P equals 50%, and since we're doing a two-tailed test, we don't think it's 50%. It could be more, it could be less. Our alternative hypothesis is that the population proportion does not equal 50%. Q is 1 minus P, is also 50%. Our region of rejection, or our critical value, since we're doing a two-tailed test at the 0.05 level, is 1.96 plus or minus. So we're going to reject our null hypothesis if the z-value that we compute is greater than plus or minus 1.96. Our formula is to compute z, take the sample proportion, subtract from it the population proportion, and divide by the standard error of the proportion, which is p times q over n. Substituting the values, the sample proportion is 66%, our population proportion, or a hypothesized population proportion, is 50%, and our standard error of the proportion is 50% times 50% over 64. This will give you a 16-point difference divided by an expected difference of 6%, which will give you a z-value equal to plus 2.66. Our rule of rejection was that we'll reject the null hypothesis, that there is no home team advantage, that it's 50-50, if we get a z-value greater than plus or minus 1.96, 2.66 is greater than 1.966, so we reject 1.96, so we reject our null hypothesis and conclude the home team has an advantage. There is a difference. It's not 50%. It's something different. Looks like it's the home team has an advantage of somewhere around 16 percentage points. Our final example of a binomial test gives a type of research which is very significant. Men, when they reach a certain age, need to take a PSA test, prostate-specific antigen. That's what PSA stands for. The current tests that are given to men fails to detect cancer in 20%. So our population proportion for whom cancer is not detected is 20%. Someone develops a new method, and we got to improve on this 20%. That's quite a few people who have cancer who are told that they don't. And this person's new method was used on a sample of 140 people, and it failed to detect cancer in 12 cases, which gives us a failure rate, 12 divided by 140, of a sample proportion of 9%. So this is a binomial test because men are classified as you either have cancer or you don't. They're put into two categories. And we want to know what the proportions of one test's classification differ from the proportions of another test's classifications. That 11-point difference is pretty substantial. That's a lot more men who will be told that they have cancer when they do, like fewer mistakes. Q, our population proportion, is 1 minus P. Q equals 0.80. And we want to know, again, what we want to know is the new method better than the old one? Is the failure rate less? Use a two-tailed test at the 0.05 level. Our null hypothesis is going to be that the population proportion of men who get the new test is no better than the old. It's 20%. And our alternative hypothesis is that the population proportion of men who get the new test is not 20%, since we're doing a two-tailed test. We're going to reject HO if the z-test that we compute is greater than plus or minus 1.96. We've used the 0.05 level of significance. We could have used the 0.01 level, and maybe we should have, since this is a medical test and it's a fairly serious outcome. We don't want to say the test is better when it's not. So maybe we should have used the 0.01. In that case, if we had used the 0.01 level, then we would have had to have been greater than plus or minus 2.58. If we had used the 0.10 level, we would have had to be, our z-value would have to have been greater than 1.65. But we used the 0.05 level. That's our likelihood that we're going to make a type 1 error, saying that the methods are different when they are not. We're going to use the z-test. Our formula says take the sample proportion, subtract from it the population proportion, as stated in our null hypothesis, and divide by the standard error of the proportion, which is the square root of population proportion times its complement divided by n. So PQ over n is how we compute the variance of a proportion, and take the square root of PQ over n, and we get the standard deviation of a proportion. So when we substitute our values, we're going to have 9% minus 20%, and we're going to divide that by the square root of the variance of the proportion, which is 20% times its complement, 80%, divided by our sample size, which is 140. This will give us a difference of 11% and an expected difference of 3%. And our question is this 11% large enough for us to say that one method really is different from another? Or is that difference of 11% simply due to sampling error? So when you divide the expected standard error, this expected difference, into the actual difference that you got, you will get a z-value equal to negative 3.66, which is far to the left of negative 1.96, and we reject the null hypothesis. And conclude that the new method is better than the old, or it's different, and in fact better than the old method. I want to say one final thing about proportions and variance of proportions. When we were studying the variance with ratio data or interval data, we found deviation scores. We squared the deviation scores. We divided by n minus 1, the number of people in our sample minus 1, and that gave us our variance. And then we took the square root of that, and we got our sample standard deviation. When you're dealing with proportions from a sample, you take the proportion of people in one classification times the proportion of people in the other classification, or its complement, and you divide by the number of people in the sample. That is the variance. That would be the variance of a proportion and if you take the square root of that, you get the standard error of a proportion. What's interesting is that when you're dealing with proportions, your maximum variance occurs when you're dealing with people or stimuli or places or things where 50% fall into each category. So 0.50 times 0.50 divided by n would be 0.250 divided by n, and this will give us the largest possible variance. If, for example, our classifications were 0.90 times its complement 10% divided by n, then we would have 0.09 divided by n as our variance. And this variance is much greater than this variance. So maximum variance when you're dealing with proportions occurs when you're in a 50-50 situation. You would think that 90% versus 10% would be larger. It's not. If 90% of people feel a particular way, we have less variance than if 50% felt one way and 50% felt the other way.